So let's review some of the concepts that we went over in class. We started learning how to draw line angle structures. So in this representation, we're not going to draw in our carbons. So the carbons are going to be represented by either the end of a line or an angle. And our hydrogens that are directly attached to carbon, we're also not going to draw those in. Any hydrogens that are attached to heteroatoms, those are going to be explicit and we will draw those in. So let's look at a few examples. The first one is this 5-membered ring structure. And I think anytime you have a ring, that's the best place to start. So we have a 5-membered ring. We can go ahead and draw just a pentagon. That will give us a good start. Now, what we can do is we can circle all of the hydrogens that are going to be implicit, meaning directly attached to carbon that we're not going to worry about drawing in. So this hydrogen, all of these that are directly attached to carbon, we're not going to worry about when we're drawing the line angle structures. The one that's on oxygen has to stay. So let's draw everything in that's left. On this first carbon here, we're not going to draw in that hydrogen, but we do have a hydroxyl group or an alcohol. All the other carbons going around, we don't have to draw in the hydrogens coming off of those carbons. But we do have a carbon directly attached to this carbon of the ring. So we do need to draw that in, and we'll just draw that in as a line. One other thing you can do when you're drawing rings especially is you can number the carbons to make sure you get the groups on the right carbon of the ring. So that's our structure. Let's look at a slightly more challenging problem. And again, I always recommend starting from the ring. We have a 6-member ring that has double bonds, so this is going to be an aromatic or arene ring. Let's draw that first. So a 6-membered ring, and we still need to draw in the double bonds because those are important. So this 6-membered ring is directly attached to another 6-membered ring that does not have double bonds. We can draw that in. Now let's figure out which hydrogens we need to draw in our structure and which ones we can ignore. So again, the ones that are directly attached to carbon, we don't have to worry about. Those are implicit. When we're looking at the line angle structure, we can assume that carbon is going to fulfill its octet, and those hydrogens are there. We don't need to draw on this one or any of those. Okay. So let's go around the ring and see. So I'm going to actually number this one as 1, 2, 3, 4, 5, 6. On 1, 2, and 3, we have hydrogens that we don't need to draw in. But on carbon 4, we have OH that we need to draw in. Now it's up to you if you want to draw in your lone pairs. For this semester, I recommend drawing in your lone pairs, even though you don't have to for the line angle structure. Let's look at the other ring. Why don't we number that one as well? So 1, 2, 3, 4, 5, and 6. And let's see. So we don't have anything attached to 6 and 5, just other carbons. We're fine there. If we look at carbon 4, we have hydrogens attached, so we don't have to worry about that. Same with 3 and 2. With carbon 1, we do have another carbon there, so we can draw one line like this. That carbon has one hydrogen and 2 other carbons. So the hydrogen we don't have to draw in, but the 2 other carbons we draw in like that. So this is our final structure. What if we're going in the other direction? We want to start with the line angle formula, and we want to figure out what the molecular formula is. So we need to figure out how many implicit hydrogens we have. So I recommend starting with the number of carbons we have first, since that's the easiest thing to count. So we have 1, 2, 3, 4, 5, 6, 7. We have 8 carbons. We're good there. Now we need to figure out how many implicit hydrogens we have on each of the carbons. For example, let's look here. We have a carbon that's directly attached to one more carbon. In order to get the octet number of electrons, we need to have 3 more hydrogens attached there. So we can do this one of 2 ways. We can either just write a 3 or we can go ahead and draw them in. So we have 3 there. Here on this next carbon we have 1, 2, 3 things attached. So there's another hydrogen there. On this one we have 1, 2, 3. Okay. This carbon we already have 3 things attached. On this next one we have 2, so in order to get an octet we have to have 2 more attached. Here we only have 1 carbon, so we need to add 3 hydrogens here. Here we have 2 hydrogens. And on this last one we have 3 hydrogens. So since we only have carbon and hydrogen in this structure, we can go ahead and just count the number of hydrogens. And if we count that up, we get a total of 18 hydrogens. And our formula for this is going to be C8H18. Okay, so one method is just going ahead and drawing in the implicit hydrogens. Let's look at something else and do the same thing. Right? Here we have a triple bond. So this is a carbon. It already has 3 bonds to it. So remember that each of those bonds counts as 1, all right, or 2 electrons. And we need to add 1 more to gain an octet, right? This carbon next door already has 1, 2, 3, 4 bonds to it. So we're good there. This one has 2, so we need to add in 2 more. This carbon next door has 1, 2, 3 bonds to it. So we have 1 hydrogen here to gain an octet. The same as the carbon next door. We already have 3 bonds to that carbon. We need 1 more hydrogen there for an octet. And here we have 2. So we've drawn in all of our implicit hydrogens. We can now come up with a formula. So if we count our carbons, we have 1, 2, 3, 4, 5, 6. If we count our hydrogens, we have 8. 1, 2, 3, 4, 5, 6, 7. And don't forget the one that's on the oxygen. And we have 1 oxygen. Another example. Same thing, we're going to draw in all of the implicit hydrogens. So on this aromatic ring, for this carbon here, we already have 3 bonds to it, so there's going to be 1 hydrogen there. Same for the other carbons that are directly on the aromatic ring. Okay, this carbon already has 4 bonds to it. It has a double bond and 2 single bonds, so we're good there. And here we need to add a hydrogen. Here there's a hydrogen. Here and here. This carbon already has 4 bonds to it, so we're good with the octet rule there. So if we count up our carbons, we have 11 of them, so C11. For hydrogens, we have 9 of them. We have 1 nitrogen, and we have 2 oxygens, so 1 on the carbonyl and 1 on the alcohol. So another thing we talked about was isomers. The difference between a molecule being the same or having the same formula but having a different structure or different connectivity. So those are called constitutional isomers. Same formula but different connectivity of the atoms in the molecule. So my question is, are these 2 molecules that I have shown the same or are they different? And one way we can start approaching this problem is, let's go ahead and just count the longest chain. All right. So here we have 1, 2, 3, 4, 5, 6 as our long chain. And then we have this CH3 on carbon 4. Let's do the same thing with the other molecule and see if we have the same thing. So 1, 2, 3, 4, 5, 6. So the length of the chain is the same. Now we need to figure out if this CH3 is in the same place or if it's in a different place. So I've numbered it one way. Let's try numbering it from the other end to make sure we didn't overlook anything. If we numbered it this way, 1, 2, 3, 4, 5, 6, we see that that CH3 is on the same carbon. It's on carbon 4. So these are in fact the same molecule. They're not isomers. It's just rotated.